And we're back, calc babies. So part B, chapter 8, section 5, partial fractions. I can remember being in an auditorium when I was an undergrad thinking, man, there's so many different techniques. Like, why all of these different techniques? But it only occurred to me later, after kind of being able to sit back and reminisce on what I learned, that really people sat around for a century waiting for a technique like this to save them time. And we are burdened by learning this technique, but you realize that this is a life hack, is really, if you think about it, that you can decompose some integrand that you really don't want to mess with into some partial fractions that you can then integrate with ease, right? This is a life hack from 300 years ago or so. I think it was Leibniz. I think it was Leibniz or one of the Bernoulli brothers, maybe. I don't know who is credited with this technique, but nevertheless, as I said, if you were in the maths, in the sciences, you would have been waiting a long time for this technique, and it would have saved you a lot of time. So let's continue. Let's do another one. Let's make this one will be a little bit harder. So the idea is the same. If you were running through your steps again, so step 1 is done. We meet the conditions to use partial fraction decompositions. Step 2 is we're going to have to go ahead and factor. And I'm looking at my x squared minus x times x squared plus 4. So x squared minus x times x squared plus 4. The only thing that I can do to factor that is I can factor an x out of that first factor, right? So this would be x minus 1. Just note, I only factored x out of this first factor. So I still have my x squared plus 4. Okay, so that is the factored form of that denominator. And I want to stay here for just a second as I'm going to go down the line and make sure that everything is either linear or quadratic. And let's go. So x, well, the factor of x is linear. The factor of x minus 1 is linear. The factor of x squared plus 4 is quadratic, right? And it is an irreducible quadratic. So we're not dealing with, by the way, that if you have to reference that, you're basically just referencing you can Google this on your own time, but it's just a matter of using the discriminant to see the types of roots that this quadratic would give you, right? Because if you think about it, is it two distinct but real, imaginary, so forth. So this, right now, let's just stay with this problem. This is I have 3 factors. 2 of them are linear, and then 1 of them is a quadratic. Okay. So you know the game plan. At this stage, I'm going to go ahead and take my 2x cubed minus 4x minus 8. This is the form that I don't like. And from here, I want to go ahead and start to set up my partial fractions here. So let's start with the first factor. That's just x. So I'm going to need some value, we'll call it a over x. Now let's go to my next factor, which is also linear. So we'll just say plus some value, we'll call it b over x minus 1 plus, and now how do we deal with a quadratic, right? Because we haven't seen this yet. So bear with me, I'm going to go back to this page where it shows us how to set up quadratic factors. So step 4, it says for each factor of the form ax squared plus bx plus c to the power of n. Now in our case, it's just x squared plus 4, right? It's not x squared plus 4 to the power of something. The n is 1, in other words. The partial fraction decomposition must include the following sum of n fractions. So since in our case, the case that we're dealing, our case n is just 1, right? Because it was simply x squared plus 4 to the power of 1. So in this case, since n is only equal to 1, we're just going to need one of these, one of those sums. We don't need to go any farther than that. So we're going to have plus cx plus d over x squared plus 4. Okay, so remember the cx, if you have to, you can rewind the video to take a closer look at how we deal with quadratic factors. But we do need two real numbers, c as well as x plus d. Okay. And now the game plan is the same. We're going to multiply both sides of this equation by the LCD x times x minus 1 times x squared plus 4. And let's go down the line. So the first round of distributing just cancels out the denominators, leaving me with 2x cubed minus 4x minus 8. All right, the second round of distributing, the x's cancel, leaving me with a times x minus 1 times x squared plus 4. All right, third round of distributing, the x minus 1s will cancel, so this will leave me with b times x squared plus 4. And finally, that last round of distributing, the x squared plus 4s will cancel, so that's going to leave me with cx plus d. I know. Let's just move down. Plus cx plus d times, well, what's left? Well, the x squared plus 4's cancel, so that's just going to be times x minus 1. Okay? Sorry I couldn't fit all that in one line. I probably could have if I would have wrote smaller. But let me go ahead and kind of give you a roadmap of where this is going to go. Because normally when all of your factors are linear, you can just use those techniques like we were using in the previous problems where you cancel A, you cancel B, you cancel C by choosing X values. But when you have a quadratic factor, more than likely what you're going to end up needing is a system of equations. Okay? So let me go ahead and see what I can do so far though. So at first let me see if I can solve for A. Right, and to do that, I would want to choose an x value of, well, look, I would want B to zero out. I would want the cx plus d to zero out. So I'm thinking about what could I choose for x. Well, maybe you're thinking what I'm thinking. If I choose x is 0, right, then that 0 when I place the 0 right here, that would zero all of that term out, including the b. Likewise, if I put a 0 here, that would zero out that entire term. So in this case, I want to solve for a by letting x equal 0. Okay, so my apologies, but on your own time, you can plug everything in, plug 0 in for all x values. I need to get us to our result. So we would find out that a is equal to positive 2. All right, and now let's see if we can solve for b by choosing an x value. All right, so we need an x value that would zero everything else out, every variable out, except b. All right, let's see if you're thinking what I'm thinking. So if I choose 1, then by placing a 1 here, that would zero all of the cx plus d out, and that same value of 1 would zero out everything where a is located. It would not do that for my b term, so that is perfect. So I'm going to, by allowing x to equal 1, I'm going to accomplish my goal. And in this case, if you plug 1 in for x and solve for b, you would find out that b is equal to negative 2. All right. So as I mentioned just a second ago, normally when you have quadratics like this, you're going to end up setting up a system of equations to solve for what is above the quadratic. So this, in order to solve for c and d, here's what we're going to do. So to solve for c and d, let's use some facts. We're going to use the fact that a is equal to 2, b is equal to negative 2, and we want to choose some value of x, right? We don't want to choose the same values of x that we've already chosen because that'll cancel out the c and the d. So we want to, and we're going to let x equal, and now I'm pausing here because it is somewhat arbitrary what you choose. You just don't want c and d to go away when you choose an x value, right? So let's choose x is equal to negative 1. Okay? So if I go through this problem, plugging in 2 for a, negative 2 for b, and negative 1 for x, then what do I get? Well, I get I'll write some of this. So this is going to be negative 6 is equal to what do we got? 2, a is 2. If I plug in negative 1, I get negative 2. If I plug in negative 1, I get negative 1 squared is 1 plus 4 is 5. Okay, plus, now I'm plugging in negative 2 for b, negative 1 for x, and negative 1 squared plus 4 again is 5. Plus, all right, well, c times negative 1, right, x is negative 1, so this ends up being negative c plus d, and then times negative 1 times negative 1 minus 1 is negative 2. Okay, so let me go ahead and capture all of that. I'll erase all of that in just a second, but let me capture all of that. So that ends up being, once you do a little bit of arithmetic, it ends up being 2 is equal to negative c plus d. Right, so this is some linear equation. Now, we're going to have to do that again. Right, I told you we're going to have to set up a system. So we're going to do that again. So again, but this time we'll have to choose a different x value. All right, so we have a is obviously 2, b is negative 2. And this time I'm going to let x equal positive 2. All right, so here was the first linear equation in our system. And now I'm just gonna, if you don't mind, with your permission, not that you even have the chance to object, but I'm gonna, if you were to plug in each of these values for a, b, and x, you would get the following linear system. 8 is equal to 2c plus d. All right, now that's what we needed. In order to, because remember our goal was to figure out what is c, what is d. By the way, you do understand we have not integrated yet. This is all just simplifying our integrand. We're almost there. So if we set up a system of linear equations, I'm going to go ahead and set it up the way you've probably seen it before. So I'll put the variables on the left side and the constants on the right side. So that would be negative c plus d is equal to 2, and then 2c plus d is equal to 8. All right, now if you at this point you can use your well, you can use substitution method, elimination method. You can graph the two linear equations and figure out the point of intersection. You can set them up as a matrix and row reduce your matrix. You can use the inverse of that matrix to solve. There's lots of things that you could do, but when all is said and done, you should figure out that c is equal to 2 and that d is equal to 4. So now, obviously I don't have the room to integrate on this page, but I do have the room to be able to rewrite the new integral. And what is that? Well, the new integral is going to be, now that I know what a is and b is and c as well as c and d, let's go ahead and rewrite the new integral. So it would be 2 over x minus 2 over x minus 1 plus 2x over x squared plus 4 I'll tell you what I'll do. I'll write it. I don't want to skip steps. So that's 2x plus 4 over x squared plus 4 dx. All right, so this guy is going to come with me on a ride to another page, And let me see if I can, yeah, let's see here. Let's see if I can. Finish this up. Ready? Beautiful. Okay, so now we want to integrate. So what I was saying, what I was about to write just a second ago is that you can split that into two different fractions, so that you have the integral of 2 over x minus 2 over x minus 1 plus 2x over x squared plus 4 plus 4 over x squared plus 4. dx, okay? So I know at this stage well, I'm actually highly impressed if you are still with me on this ride, but the good news is you can now integrate this. I mean, this is integration that you would have learned in previous lectures, and I'm just going to go through and just give you the result. So the result should be 2 ln of x minus 2 ln of x minus 1 plus, that would be ln of x squared plus 4, and that is an arctan, so that would be 2 arctan of x over 2 plus c. Voila. All right. So that is the idea of using partial fractions to simplify your integrands, to make your integration process easier. I will see you at another time.